Hello viewers, Wagdaruna taking you through the story for A-Level Physics Paper 2. And this video I'm going to go through the part of Wheatstone's bridge. So this video is under the topic of current electricity and is suitable for students in both Senior 5 and Senior 6 offering physics as part of their combination. So before we go to the topic, let's first look at the course outline for this paper. So physics paper 2 is divided into 4 parts. The first part is geometrical optics, where 2 questions come from these topics and the student must answer 1. The second part is physical optics or waves, and where 2 questions come from these topics and the student must answer 1. The third part is electrostatics and electricity, where 3 questions come from these topics. And the fourth part is magnetism and alternating current, where 3 questions come from these topics. So previously we had already covered the electrostatics, capacitors, and now we are on current electricity. So in current electricity, what is teach was already covered. Part 1 was covered, part 2, part 3, part 4, part 5, part 6, part 7, and now we are on part 8, which is Wheatstone bridge. So in this video, you're interested in calculations, but full complete notes are available in this book, Mastering A-Level Physics, Paper 2. It contains clear notes, worked examples, and trial questions of all the topics in Paper 2. Also, other books are available. For example, if you offer physics at A-Level, you'll need 3 books. There is Mastering A-Level Physics Paper 1, Mastering A-Level Physics Paper 2, and also a topical question bank. If you offer principal mathematics, then you need also 3 books: Mastering A-Level Mathematics Paper 1, Mastering A-Level Mathematics Paper 2, and also a topical question bank. If you offer subsidiary math, you'll need 1 book, and that is Mastering A-Level Subsidiary Mathematics. Then the rest are for O-Level Physics and O-Level Math. So now we can start our topic of a Wheatstone bridge. So a Wheatstone bridge consists of 3 variable resistors, R1, R2, and R4, and an unknown resistor, R3. So just see how it looks like, but let's look at this balance condition of a Wheatstone bridge. So this is the circuit of how a Wheatstone bridge resistors in a Wheatstone bridge are set up. So there are 4 resistors. There is R1, which is this, and it is variable. There is R2, which is that, and there is R3, which is that, and there is R4, which is that. So the word balance condition means, okay, so let's just do this. If current is to flow from here, it would reach here and split. One goes this side through R1, another one goes this side through R3. Then if it reaches here, there's also another junction. It would split. One goes this side, another one goes this side. Okay, but also at this point, it would also split. Or if not, one would join here and go this side. So this and this would join to go through this R1, R2, and this goes through R4, and then back to the source. Okay, but in this, what we call balance condition, our interest is to make sure that no current goes through this galvanometer. That is why these resistors are variable, so they will be adjusted until the potential at B is the same potential at D. And when that happens, it implies that all the current which pass through R1 will be the same current to go through R2. And also all the current which pass through R3 will be the same current to go through R4. and no current will go through the galvanometer. That means this galvanometer will show no deflection. So that is our aim when we talk about balance condition of a Wheatstone bridge. So this current I1 will come and split at this point I1, I2, and here there will be IG. So our aim is that IG is negative, is 0. So you shall come and say that one variable resistor, say R1, is adjusted until current through the galvanometer connected between B and D is 0. So that's our aim, that no current goes through the galvanometer. And when that happens, it implies that the potential at B is equal to potential at D. Because the potential are the same, it implies that the PD, let us go back to the circuit. Now, because this potential is and at this point and this point are the same, it implies that PD across R1 is equal to PD across R3. Similarly, PD across R2 is equal to PD across R4. So that knowledge shall go back here and we shall say PD across R1 is equal to PD across R3. Therefore, I1 R1 is equal to I2 R3. Similarly, also I1 passes through R2 and I2 passes through R4. So this should be R4. So that means that PD across R2 is equal to PD across R4. Therefore, I1 R2 is equal to I2 R4. So when I divide these two equations, equation 1 by equation 2, I'll come up with this. Then I realize that this I1 can cancel and this I2 can cancel. So what we remain with is what we call the balance condition of a Wheatstone bridge. So in short, if you look at this circuit and they tell you that the Wheatstone bridge is balanced, it implies that this over this is equal to this over that. So the order matters. If you say R1 over R3, then you have interchanged everything. So the best way is to say this resistor here divided by the resistor which is here will be equal to the resistor here divided by this resistor at that point. So the order matters in this balance condition. So now that we have looked at the balance condition, we shall go through these questions. Question 1 says, in the circuit below, the galvanometer shows no deflection. Know this word, no deflection, meaning that already the Wheatstone bridge is balanced. Shows no deflection when the 50 ohm resistor is shunted. Shunted means they connect it in parallel with a resistance R, as you can see it here. So shunted means you connect them in parallel. Find the value of R. So just like we saw, for the balance condition of a Wheatstone bridge, we don't need the EMF, the value of the EMF. Our interest is that are all these values given. If it's true, then it's already you can use the balance condition. So when 50 ohm resistor is shunted with R, we shall be able to get the effective resistance, which is R1 is equal to product over sum. Okay, so when the galvanometer shows no deflection, it implies that 25 over R1 is equal to 10 over 5. So let's see how it comes about. Remember we said that for this to be balanced, what is here must be divided by what is here. And with this combined one was R1, that's why we say 25 over R1 equal to what is here divided by what is here. That is why we said 10 over 5. So that is where this is coming from. So here it is only one unknown, so we can rearrange and make it the subject. So that is R1, but they want the value of R, so we shall go back to R equation 1 and substitute for R1, cross multiply, divide through by 12.5, then collect like terms and make the get the value of R, and that's what they wanted. Then question 2 says, in a Wheatstone bridge below, the ratio arms, these are called ratio arms, so the ratio arms R1 and R3 are approximately equal. When R2 is equal to 500 ohm, the bridge is balanced. On interchanging R1 and R3, the value of R2 for balancing is 505. Find the value of R4. So the circuit they've given us. So at this point, before interchanging, we shall have R1 over R2 equal to R3 over R4. So let's first write that. So before interchanging, R1 over R2 is equal to R3 over R4. So come and substitute for R2 and make R1 the subject. Then after interchanging, it means that now this one goes here and this one goes here. So we shall come up with that. Then substitute for R2 and make and cross multiply to give you this. Now the good thing, we already know the value of R1, so come and substitute for R1. Okay, then from here this and this can cancel to remain with that. Then this one can go this side to give you R4 squared, and this times this will give you this 500. Then square root will give you the value of R4 as this, and that's what they wanted. Then question 3, in a circuit below, no current flows through the galvanometer, meaning the Wheatstone bridge is balanced. No current flows through the galvanometer when the 20 ohm resistor is shunted with the resistor of 100 ohm. So this one must be shunted with 100 ohm resistor for no current to flow through the galvanometer. Okay, when P and Q are interchanged, the shunt resistor has to be changed to 50 ohm. For G, again to indicate 0. Calculate the value of S and the ratio of P to Q. So first of all, you have to get the effective resistance of these two resistors in parallel, 20 ohm and 10 ohm. So effective resistance will be product over sum, which gives you this. Then when no current flows through the galvanometer, it implies that, let's first go back to the circuit. It implies that P divided by Q is equal to this effective one, which is now 16.67 divided by S. So you come here and write our balanced condition. To give you that as equation 1. So R1 was already here, so come and substitute and be able to get that equation. So let's first write equation 1. Then on interchanging, when this is shunted with this, the effective resistance will be product over sum, which is that. Therefore, when they are interchanged, it implies that now these ones will change. So Q will go up, P will go down, and this R1 will be replaced by R2. To come up with this, substitute for R2. Then, but remember, here we have the equation 1 is in form of P over Q, meaning here we also get the reciprocal this side and also reciprocal this side to give you this equation 2. So that means that I can equate to get S as the only unknown, and S will be equal to that. What about the ratio? So from equation 2, substitute for S and come up with this. Therefore, the ratio will be this to 1. And that's what they wanted. Then question 4, the diagram below shows an imbalanced Wheatstone bridge. Imbalanced. Okay. Imbalanced means current still goes through this. The temperature coefficient of the coil is this per Kelvin. The resistance of the coil at 12 degrees Celsius is 9 ohm. Find the temperature to which the coil has to be raised for the bridge to balance. Remember, it was imbalanced. It was imbalanced, so this one we have to raise the temperature. When you raise the temperature, the resistance also changes. That means that we have to first get this resistance. So for balance, this one over what is here is equal to this over what is here. So let theta be the temperature at balance and R theta be the corresponding resistance. So this one should be resistance. So R theta over 8 is equal to 8 over 7. So what you have done, it is the same if you look at this. For me, I began from the other side, but it's still okay. Remember, you can say this over this divided by this over this, or you can choose to reverse and say this over this divided by this over this, as long as you are consistent. So that's what I've done, and I'm able to get the value of R theta as that. But we know that R theta is equal to R naught in brackets 1 plus alpha theta, where this alpha is the temperature coefficient of resistance. So what I'm going to do, I'll substitute for R theta, substitute for alpha, which is the temperature coefficient of resistance, and this is unknown. This is unknown, and also R naught is unknown. Also, we know that R12 is equal to R naught in brackets 1 plus temperature coefficient of resistance times 12. So R12 is 9, meaning that when I simplify this in brackets, I'll come up with 1.24. That means that the value of R naught is this. So I'll come here and substitute for R naught in equation 1 to give you that step. Now here is only theta which is unknown, so I'll have to look for making the subject. First of all, I'll take this one this side by multiplying by that, by the reciprocal. Then this one is the same as 0.02 theta. So when I take this one this side, I'll come up with this equal to that. Then I make theta the subject, and that will be the answer they wanted. So that brings us to the end of this video. Thank you for watching, and be reminded the next video will be on meter bridge. So if you have not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video on meter bridge has been uploaded. And also, if you know of any student who is not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp so that we can all benefit as a family.